Okay, let's do an example problem in which something is sliding to a stop with friction. Okay. Now, we've done this problem before, so we've got some mass m, and it's moving with some initial velocity. Let's say the initial velocity is 2.77 meters per second. It's sliding along a rough surface in which the coefficient of kinetic friction is 0.343. And I want to know how far does it go until it stops. Okay, so x equals x naught plus v naught t plus 1/2 at squared. V equals v naught plus at. A equals F over m. The F is given by the frictional force. The frictional force, okay, is given by mu sub k times the normal. The normal is going to be equal to mg in this case. Plug everything in and solve. Okay, you all know how to do that. Okay, this is all chapter chapter 2 stuff and chapter 5 and 6 stuff. Okay, but let's solve the problem in an entirely different way. So instead of solving it that way, because that's an awful lot of steps, and we're going to be lazy and we don't want to do a whole lot of steps if we don't have to. And so we're going to do this differently. I'm going to do this with conservation of energy. I'm going to say initial energy plus final energy, initial kinetic and potential equals final plus, but we got friction, so we know there's non-conservative work in there. Okay. Now, the initial and final, it doesn't matter where you put the zero, they're the same. And so they cancel. Okay. The final kinetic energy is zero, so all this has to equal zero. Okay. So we have 1/2 mv squared. Now, what is the non-conservative work? That's the work due to friction. And so in this case, the work is going to be the integral f dx. Okay, so that's, turns out because the frictional force is constant, just going to be minus fx because the friction is the opposite direction. Okay, the frictional force, the frictional force is mu sub k times the normal. In this case, the normal is mg. And so we would say, therefore, that's negative. We would say that 1/2 mv squared minus mu sub k mgx. Okay, so the m's cancel, and we find that we do a little bit of algebra here, and x is just going to be equal to v squared over 2 mu sub k g. So that'd be 2.77 meter per second, and then that squared divided by 2.343 times 9.81 meter per second squared. And again, like I have said before, and I'll keep saying, make sure the units work. In the numerator, we have meter per second, and that's squared, so that's going to be meter squared over second squared. And the denominator is meter per second squared, so that gives you meters. So that looks like it's working. Just randomly sticking all these terms together like this is not going to make the units work out right. And so if the units do work out, there's a good chance you did the problem right. So that's always going to be the case. And so when you plug in the numbers, x turns out to be 1.14 meters. Okay. Now, next question. What if it's sliding down an incline of 15 degrees? Same thing. So V naught is still going to be 2.77 meters per second. Coefficient of kinetic friction, let's say the coefficient of kinetic friction is still 0.343. Okay, so now what? Well, we can do this the same way. Initial potential plus initial kinetic equals final potential plus final kinetic. Okay, we still have the non-conservative work because there's still friction in there. Okay, So it stops down here somewhere after it's gone some distance x. So if I put my zero of potential right there, that means the final potential energy is zero. Final kinetic energy is zero. Okay, but initial potential energy is not zero, because now it's going to be at some height h. H is obviously going to be x sine theta. So that we're going to have mg h plus 1/2 mv squared minus the force of friction times the distance. That's going to equal 0. Okay, so start f sub k. All right, so all we got to do is find, we know what h is, and so all we got to do is find the friction. Okay, well, that's going to be mu sub k times the normal. Well, what's the normal in this case? Free body diagram would tell us that the normal, okay, because here it is, we got mg, we got normal, some angle theta, so the normal is going to be mg cosine theta. Okay, all right, so mgh, or mg, times x sine theta plus 1/2 mv squared minus mu sub k mg x cosine theta equals 0. The m's all cancel. Okay, we do a little bit of algebra here. Okay, algebra here. Okay, we solve for x. Okay, and so x turns out to be v squared over 2g mu sub k cosine theta minus sine theta. Okay, so algebra. Okay, move all the x terms. So move all the terms over to we keep on one side of the equation. Move the other term to the other side of the equation, and then what we do is we solve. Okay, isolate the x. You all know how to do algebra. You plug in the numbers, and this comes out to be 5.39 meters. Okay, it takes longer to stop going downhill. Now, again, you remember this problem was considerably more difficult to do using the kinematic and force equations than it is here, I think, using the energy equations. So again, this is a case where the energy considerations actually make this problem a little bit simpler to solve, at least in my opinion. And so it's something to think about. On a test, if I say solve the problem, I don't really care which method you do to solve it. You just have to do it correctly and get the correct answer.